Good day and welcome back. Today is Lecture 6-2 on metric path planning. Typically, humans probably do more topological path planning where they navigate by looking for landmarks. However, when you're going a long distance and you're using a map or GPS, you may use a little bit of a combination of topological and metric path planning. In metric path planning, the robot navigates by measurements as well as odometry and ranges. Just like with topological path planning, anything that involves too much sensor or odometry is going to have some error. But that's what we're going to talk about today, is how to design a metric path planner for the robot. You will be doing topological and metric path planning, as well as localization and mapping on your final project. The objectives of today's lecture are to describe metric navigation, as well as wavefront propagation, and potential field navigation. We've already seen a little bit of potential fields method when we talked about obstacle avoidance and reactive control several weeks ago, but this is looking at it from more of a path planning perspective. And also how to apply wavefront planners such as Trulla for path planning. Wavefront propagation or expansion or Grassfire is an efficient and simple to implement technique for finding routes in fixed size cell arrays. It employs wavefront expansion from the goal position outward, marking each cell's distance to the goal. It can be a 4 neighborhood or an 8 neighborhood. This continues until the wave reaches the initial position. The planner can then estimate the robot's distance to the goal, as well as recover a specific solution trajectory by linking together adjacent cells that are always closer to the goal. It's also called Grassfire Expansion or Wavefront Propagation, because you can color code the path to indicate the distance from the source or the distance to the goal. This can be done with 4 neighbors or 8 neighbors if the robot can move in diagonal directions without greatly increasing the odometry error. The result of a wavefront propagation in a map is it looks like a potential field. The path itself represents what the robot should do as a sensor observation. Any undesirable terrain is shown on the Trulla planner as gray. Obstacles in black and open areas are in white. Path planning and reactive execution. Most path planning algorithms are employed in a plan once and then reactively executed, which is a type of hybrid control. The problems with reactive execution are sub-goal obsession, which means the robot gets stuck trying to get to a sub-goal when that's not really the overall goal. Lack of opportunistic replanning, which means that as the robot's moving, it cannot immediately make a new plan if it's not making progress. One way to correct for this is to use a D-star algorithm, which has continuous replanning. Potential field path planning creates a field or gradient across the robot's map that directs the robot to the goal position from multiple prior positions. We've discussed this before. The robot is treated as a point under the influence of an artificial potential field, and it generates robot movement, which is similar to a ball rolling down a hill. The goal generates the attractive force, and the obstacles are repulsive forces. The superposition of all forces is applied to the robot. Artificial potential fields smoothly guide the robot toward the goal while simultaneously avoiding obstacles. Here is a model of a potential field path planning where obstacles are modeled as repel vectors and goals are modeled as attractor vectors, and by applying it over the entire space, it is possible to create a path plan from any of the robot's start positions. Local minima. A local minima occurs when the robot gets stuck due to counteracting forces. To overcome a local minima, add a field from the source to push away from it, introduce noise into the environment, and the outward source may still lead to local minima, but noise may overcome this. Here is an example of injecting noise in order to move the robot to the goal. Notice sometimes it's also possible to use a timer or a state machine to cause the robot to switch states to get to the goal. Random noise. The path will vary depending on the random values of the noise vector, but note that too much noise will not work and the path will not be found, as shown in the right figure here. There can also be counteracting fields. Another challenge with potential field path planning is counteracting fields. When there are too many boundaries or obstacles, some of the attractors and repel vectors may start to cancel each other out. Depending upon the strength and number, noise or a timer or a state machine may or may not correct for this problem. Potential fields cannot handle multiple goals due to the aforementioned challenges of local minima and counteracting fields. This concludes today's lecture on metric path planning. Have a robotastic day.